Hello, sir. This is a report on oil spill cleanup from seawater, which is submitted by Gopal Verma, Gurjit Singh, Harsh Kumar Singh, and Harsh Kartike Singh. So, let us begin with an introduction. An oil spill is basically the release of a liquid petroleum hydrocarbon into the environment, especially marine areas, due to human activities, and is a form of major pollution in the neighboring areas. The oil spill is majorly caused due to release of crude oil, offshore platforms, drilling rigs, and as well as spills of refined petroleum products. The cleanup of oil spill is very difficult nowadays and is a major challenge in front of many scientists. And it may even take weeks and months or even years to clean up the oil spill. Now let us move on to major effects of oil spills, which are on local industries, which depends highly on marine resources for their raw materials. The second one is human health. Seafoods form a major part of human appetite, and if petrol enters the food chain, then it will have a devastating effect on human life. Oil spill prevent the exchange of oxygen in air with water, and hence the marine life slowly chokes to death. Hence, it damages the beaches, kills the vegetation in marshlands and mangroves, thus making fragile ecosystems. Now, let us have let us move on to oil spill cleanup using immersed metal wool. Now, the purpose of the current study is to demonstrate the fact that a thin porous metal wool layer immersed in the liquid fuel provides a second mode of heat transfer, collecting the heat from the gas phase on high heat flux regions and transmitting it laterally towards the center. This causes the average regression rate to increase by an order of magnitude, thereby promoting faster combustion. The heat transfer and mass transfer are further coupled by two-phase flow effects that occur on the surface of the metal wires immersed in the liquid layer. The problem description is as follows. As in the diagram given, the geometry of the geometry of the depicted problem is divided into three layers. The upper layer includes thermal conductive metal wool and fuel, the porous media. The middle layer is composed of the fuel alone, which is the cause of pollution, and the bottom layer is composed of water, mainly marine or seawater. As the fuel burns, the metal wool dissipates the heat horizontally in the x direction and as well as in the vertical direction or in the y direction, thus enhancing the fuel evaporation. The heat is dissipated to the fuel layer below the metal wool and then to the water layer. As in the diagram shown, m dash represents the mass flow rate of fuel into the atmosphere, while q double dash demonstrates the heat flux which is given to the fuel through the metal wire and through the metal wire wool. The assumptions made in the development of the model are: the metal wool is homogeneous. It is homogeneous about its length and about the area. The density, specific heat, and the thermal conductivity of fuel and water are constant, and it doesn't change with any change in temperature or pressure. In-depth radiation and the liquid convective motion are neglected for simplification of the model. Our approach to solve the problem is as follows. We would be doing the mathematical modeling at small scale that can be scaled up. The model would be validated using an experimental setup comprising of a 10 centimeter diameter and 5 centimeter deep stainless steel vessel filled with water to a depth of 4 centimeter and fuel, which is dodecane, of 1 centimeter thickness. The aluminium metal wool with thickness of 0.25 and 0.5 centimeter is then placed on the fuel layer to form a three-layered geometry as shown in the figure on the next slide. This is the basic setup of our model. Delta represents the thickness of the metal wire, which ranges from 0.25 to 0.5 centimeter. LF is the depth of fuel column, which is equal to 1 centimeter, Lw is the depth of is the thickness of water layer, which is 4 centimeter, and L is the total length of the fuel of the liquid column along with the metal wire. These are the thermophysical properties of fuel, dodecane, and aluminium that would be used in our calculations are known: density of fuel, specific heat of metal wire, saturation temperature for dodecane only, specific heat of fuel, thermal conductivity of metal and fuel, emissivity of fuel and wire, Stephen-Boltzmann constant of for dodecane only, and heat of vaporization for dodecane only. The remaining will be continued in the next report. In the next report, we will make computation models in which we will apply equations of heat transfers in order to calculate the rate of evaporation of oil from water surface. We will also try to find out any other element other than aluminium which will enhance enhance the efficiency of our model. We thank you, sir, for your precious time and have a good day, sir.